The next theorem says if R is a ring with unity 1, then the mapping from the integers to that ring given by this is a ring homomorphism. So if we take an integer n and map it to n times 1 in R, realize what this means. N is not an element of R. 1 is. We're assuming this 1 is an element of R. This does not mean n times 1 in R. It means 1 added to itself n times if n is positive. Negative 1, the additive inverse of the unity, added to itself the absolute value of n times if n is negative. And by definition, if n is 0, it means the 0 element of R. That's a ring homomorphism. And what this means is that the corollary, at least in the case where the characteristic of R is 0, R contains a subring isomorphic to the integers. An arbitrary ring with unity that has a characteristic of 0 contains a subring isomorphic to Z. Z is kind of like a core subring of any ring with unity that has a characteristic of 0. What's an example of such a ring? Oh, how about like ZX? ZX, that's the polynomial ring with coefficients in Z that has a subring isomorphic to Z. What is it? How about the constant polynomials in there? 2 as a polynomial, a constant polynomial. 3 as a constant polynomial. 0, -5. Any constant integer polynomial that forms a subring of Z, ZX isomorphic to Z. Makes sense? Pretty natural kind of thing, isn't it? And yeah, this does have a characteristic of 0. What does characteristic mean? Characteristic was, again, defined to be the smallest positive integer n in an arbitrary ring where x is a ring element such that nx is 0 for all x in the ring. Kind of similar to the concept of an order of an element in a group, but not the exact same thing. This means, again, when n is positive, it means x added to itself n times. Is there some smallest positive integer n where this is true for all x in the ring? If it's not, you could argue maybe you should say the characteristic is infinity, but for some technical reasons, they say the characteristic is 0. The characteristic of this ring is 0. Take an arbitrary polynomial in there and multiply it by an arbitrary integer, meaning added to itself by that many times, you're not going to get back to 0 because we're not doing any modding, right? Whereas in something like this, that has characteristic equal to n. Take a polynomial with coefficients in Zn, 0 through n minus 1, for example, if n is 10, coefficients 0 through 9. Add it to itself 10 times, mod the coefficients by 10, you're going to get a bunch of zeros, no matter what the starting polynomial is. So this ring does not have a subring isomorphic to Z, but this one does. And there are other ones that do as well. I mean, you could, instead of having Z, you could have QX or RX. Those have subrings isomorphic to Z. Not ideals isomorphic to Z. Constant polynomials in these things are subrings, but not ideals because they're not superclosed. Right? You multiply a constant polynomial by a non-constant polynomial, you will not get a constant polynomial. These are all good things to think about. Z itself is a ring, and Q and R are rings. Q and R are fields, but none of these polynomial rings are fields, right? Polynomial rings are never fields, never, ever, ever fields. But we're about to see that rational functions can form a field. Hang on. Anyway, again, re-emphasizing this corollary. If the characteristic of R is 0, then R contains a subring isomorphic to Z. If the characteristic of R is n, then R contains a subring isomorphic to Zn. Oh, yeah, that contains a subring isomorphic to Zn. The constant polynomial is in there. Another query is that any field contains ZP for some prime P or Q, the rationals. That's interesting. If F is a field of characteristic P, again, where P is assumed to be prime here, the author doesn't actually say that, does he? P is assumed to be prime because Zn is not a field when n is not prime. If F is a field of characteristic P, yes, P must be prime, then F contains a subfield isomorphic to ZP. And yes, if P is prime, ZP will be a field. If F is a field of characteristic 0, like the rationals or like the reals or like the complex numbers, then F contains a subfield isomorphic to the rationals. ZP and the rationals form sort of core fields, minimal fields, you might say, either a characteristic P or characteristic 0. Any other field is bigger than those, they contain them. And more than just bigger, they contain them, contain isomorphic copies. Yeah, the real numbers contain the rationals as a subfield. The complex numbers contain the reals as a subfield and the rationals. And yes, I did hint at the fact, and we'll talk about this a little bit more here still today, that there are fields of, for example, order 25, even though 25 is not prime. It is a square of a prime. A field of order 25, though, is not isomorphic to Z25 because Z25 is not a field because 25 is not prime. So it's some other kind of field, but it is a field. We'll talk about that more later today. And yes, this last couple pages of chapter 15 starts talking about something called the field of quotients. What's the main theorem here? Let D be an integral domain like the integers, for example. Or maybe like that. What's an integral domain? Remind yourself. Commutative ring with unity in which every that has no zero divisors, right? Not necessarily a field, but in fact, again, this is not a field. No zero divisors, though. If D is an integral domain, then there exists a field F called a field of quotients of D that contains a subring isomorphic to D. You can always create fields using integral domains is the essence of what happens in this proof. And without going into details, essentially what you're doing is you're just creating fractions out of your integral domain elements. Just like we can take integers and create fractions of integers to get rationals. So we can take, for example, the ring of polynomials with coefficients in Z, which is an integral domain, and create fractions of those things, rational functions, instead of rational numbers. Do we call it QX? No, we don't, because the coefficients in the numerator and denominator polynomials are still integers. Standard notation for it is this: ZX with parentheses instead of square brackets. This turns out to be the field of rational functions with coefficients in Z. And again, Rx, even though R is a field, the real numbers form a field, Rx is not a field. Ring of polynomials, even when the coefficients are from R, is not a field. For example, x squared, its multiplicative inverse is not a polynomial. It's 1 over x squared. It's a rational function. You can still, though, create the field of rational functions. That's the field of rational functions with coefficients in R. So that allows for irrational coefficients like square root of 2 and pi and e and that kind of thing. I guess you could also say it must be the case that you could think of Zx as a subfield of Rx, right? Every rational function with integer coefficients is also a rational function with real coefficients because integers are reals. Wow. Lots of wild kinds of things going on in your mind here, or my mind here, that I'm saying. and trying to communicate to your minds to start bouncing around in your mind here. Hopefully not having nightmares, but sweet dreams about them or something.